Okay, so welcome to the second class. And in the last class, we completed till isotopes, atomic number, and mass numbers. Okay, so from there, uh, now let us start nature of matter and energy. Okay, and let us start with the classical theories of light. You know that there was a lot of debate earlier about light, right? Whether light is a particle, light is a wave, right?
No, I did not know that.
Okay, so remember that light has a dual behavior. Okay, so it can behave as a wave as well as it can behave as a particle. Okay, so Newton believed that light was composed of tiny particles, which he called corpuscles. That is tiny particles.
Okay.
And there was another scientist, Huygens, right? Huygens, what that scientist question he conducted, and that led him to theorize that light is a wave. Okay, and Huygens was like a small scientist or a smaller scientist in compared to that of Newton. So what Newton said was considered to be like the true nature of physics, right?
Yeah.
So so Newton believed that light is like a particle. Huygens believed that light was a wave. He also proved it with the properties like refraction, diffraction, reflection, right?
Yeah.
In the mid of 19th century, physicist James Maxwell proposed a theory regarding the properties of magnetism, light, and electricity. Maxwell theorized that light could act on charged particles because it existed as an electromagnetic waves made up of magnetic and electric field. Over time, Maxwell electromagnetic wave gained wide acceptance and came to be the classical theory of light. According to Maxwell's theory, light is an electromagnetic wave composed of continuous wavelengths that form a spectrum. So earlier the debate was that light is a particle, light is a wave. Okay.
Hmm. Yeah.
Then came in Maxwell, who said that light is an electromagnetic wave.
Yeah.
Okay. So electromagnetic wave means it has electric nature as well as magnetic nature. Okay. And remember this continuous wavelength that forms a spectrum. Okay. So there is a continuous wavelength. So it ranges from wavelength 10 raised to minus 16 to wavelength 10 raised to 4 and ahead. Okay. So
Yeah.
what we need to remember in that is the one which has extremely low wavelength 10 raised to minus 16, 10 raised to minus 14, 10 raised to minus 12, they have very high energy. So when you have high energy, you have high penetrating power. Basically it can like burn your skin, damage your skin. Okay. Hello Arnav,
Yeah.
are you with me?
Yeah. Yeah. I'm just writing the notes. You don't have to worry if I don't respond.
Okay, no, because
I'll
I
I'll,
have
I'll tell you if I don't understand something.
no problem, but I have a habit of asking, so it's better you respond. Okay, and because we are not in front of each other, it's better you respond. Okay,
But it's
so
harder because when I'm writing the notes, it's harder to respond and focus on writing it at the same time.
no problem. uh okay, what I can do is I can ask you to write when it is absolutely required. Okay, but
But
let us
I
let us
just write
continue.
like small notes along so that I can actually remember. Otherwise, it's very easy for me to forget the stuff that is
No
being said.
problem, as you are comfortable. I'm okay with whatever method you follow. I'll try to be like, I have a habit of asking questions in between, but let us see. I think it will work, not to worry. So electromagnetic spectrum, so what I was talking about was when we have 10 raised to minus 16 wavelength and when we have 10 raised to 4. So if you have lower wavelengths, you have higher energy, and if you have higher wavelengths, that means you have lower energy. Okay. And one more point that you should remember is that one is I told you about wavelength. Other term that we can use is frequency. Okay, so
Yeah.
you know in physics that your frequency is inversely proportional to the wavelength, correct? That means if
Yeah.
wavelength is high, frequency is low. And if the frequency is high, wavelength is low, correct?
Okay.
So if you check over here, right?
Yeah.
Okay. So when you have a very high frequency, your wavelength is low, correct?
Yeah.
And when you have higher wavelength, you have lower frequency. Compare the frequency of this against this. This is 10 raised to 24. This is 10 raised to 4. Okay.
Mhm.
Does that make sense?
Yeah, that makes a lot of sense.
Okay. So now remember that these are high frequency or lower wavelength. These are lower frequency or higher wavelength. Okay. So your visible light comes in the range of lower frequencies. Okay.
Yeah.
That's the reason it is not damaging us. But we particularly know UV region is considered to be dangerous to us, right? We are not, we are supposed like we should not be exposed to UV light for a longer time, right? Are you aware of this or no?
Yeah.
Right? And that's the reason like sunscreens are recommended whenever we go in sunlight. Okay? Because sunlight also has some portion of it as UV light.
Okay.
Okay? Anyways, that is not a point of discussion, but what I wanted to tell you is that first we understood that light is particle, light is wave. Next came in Maxwell, who said that it is a electromagnetic wave. That means it has an electric component, it has a magnetic component. Correct? Now, when we
Yeah.
talk about electromagnetic wave, we talk about continuous spectrum. When we talk about continuous spectrum, it ranges from low wavelength to high wavelength. Low wavelength means higher energy, high wavelength means lower energy. Radio waves are the one which has high wavelength and they are present everywhere around us, like Wi-Fi signals, the mobile signals, everything is around us. Okay, am I clear with what I said?
Yeah.
Okay. Then at the end of the 19th century, matter and energy were considered to be distinct and unrelated entities. Matter was thought to be composed of particles that had mass and a specific position in space at a particular time. Okay. Light energy was considered to be electromagnetic wave that had no mass or specific position in space. In 1887, German physicist Heinrich Hertz was attempting to generate electromagnetic waves using induction coils and instead discovered photoelectric effect. Okay, in which light shining on the metal surface cause emissions of electron from the metal. Hertz reported the photoelectric but did not attempt to explain it. Correct? Does that make sense?
Yeah, it does.
Okay, so basically what he was trying to do, he was trying to understand what happens when electromagnetic waves, right, are uh, shines on the metal surface. And the process, he
Yeah.
observed that electrons were emitted. Okay, but he didn't try to explain that. According to classical theory of light, the intensity of the light shining on the metal should determine the kinetic energy of the electrons. Therefore, more intense the light, more energy the emitted electron should have. Okay, so basically, what that means is more the intensity, more should be the electrons that should be emitted. Is that clear?
Yeah.
So because it was believed that the intensity maximum is the intensity, maximum is the kinetic energy. However, Hertz's experiment demonstrated that frequency of light was more important in determining energy of the emitted electrons. Since classical theory of light and matter could not explain the observation, it began to be viewed as flawed. Okay, am I clear?
Yeah.
Okay, but later on came in Einstein, and Einstein was able to explain this concept, and he was awarded a Nobel Prize. Okay, then came the next scientist, that was Planck. So, so far, where are we? We are at the energy. We spoke about the wave. So wave, uh, there is particle nature, wave nature, electromagnetic waves, high energy, low energy. We discussed that. Then came the photoelectric effect, where we understood that if light is bombarded onto metal surface, electrons are emitted. These electrons are emitted are not dependent on intensity, but is dependent on the frequency. Correct?
Yeah.
Till here, are we clear?
Yeah, I'm just writing the notes for the photoelectric effect.
Yeah. Okay. So tell me when you are done. So once you are done with low frequency light, high frequency light, tell me. I want you to add one more point.
Hmm.
That was, it was believed that intensity of the light is responsible for the electron emission, but it was observed that frequency was responsible.
So the frequency determines the number of electrons that are emitted.
Frequency decides the electron emission and not the intensity.
Finished. Hello?
Then, okay.
Yeah.
Then Planck's quantum hypothesis. Now, German physicist Max Planck was studying the spectra of the light radiant energy emitted by solid bodies called black bodies. Okay, heated to incandescence glowing. When a solid is heated to a very high temperature, it begins to glow. First red, then white, then blue. The change in color and corresponding light spectra do not depend on composition of the solid. The intensity of the light of different colors can be measured and plotted on the graph to produce a curved line. Okay, classical physics predicted that energy curve should go up continuously as the temperature increases. So similar phenomenon, right? So he said that if it was classical physics, then if you keep on heating, the energy, the intensity should go on increasing exponentially. Okay.
Yeah.
But what he observed, that it reaches a peak and then it dips. It reaches a peak and then it disappears. The
Oh,
intensity keeps on fading away. Who observed this?
it's blank.
Max Planck. What did he observe? That if you heat an object, it will become, it will give a certain intensity, and after it reaches a peak, it will drop if you increase the temperature.
Okay.
Correct?
Wait,
So
peak of intensity.
intensity.
How's intensity like measured?
How is intensity measured? There are equipments which measure, like imagine a bulb glows, right? So, good question. Like there are detectors for it. I don't remember the detectors, so sorry. But for the sake of this discussion, just remember that there are detectors which detect the intensity.
And then
Okay.
what, like, as intensity increases and decreases, what properties of the like object change?
So uh, there are bulbs which are dim, and there are the bulbs which are very bright.
Yeah.
So what is the intensity. It is the same yellow light or white light that is emitted, but what is difference
Yeah.
is like one is extremely bright and other is extremely light. The frequencies are same, but the brightness is different.
So basically, what he's saying is that if you increase the heat by like a lot, it reaches
Yes.
a peak, and then eventually it gets like less bright.
Yes, so even like yeah, it disappears after some time.
Okay. Okay.
Okay, but classical theory said that if you keep on heating, the intensity should have gone increasing.
Yeah.
Okay, so compare the position of the peak. Okay, so that's fine. So Planck accounted for unexpected results of heating experiment by postulating that matter can gain or lose energy only in whole number multiples according to the equation E is equal to NHF. Can you write down this?
Is there a name for the formula, or is it just called E equals
Sorry, I
NHF?
didn't get you.
Is there a name for it specifically, or do I just write E equals NHF?
So it's a Planck's equation.
Planck's constant?
No, H is the
Oh, it's
Planck
not
constant,
constant. Yeah.
but
Okay.
this was equation was given by Planck's. So E is equal to NHF. Okay. So basically, what he proved that, or he assumed that light is getting emitted in the form of packets. Okay, and these packets are called as or quantas. So quantum, a unit of packet of energy. Plural is quanta. Okay.
Yeah.
So, so imagine this as our currencies, right? So we have different denominations. We have denomination like $100, right? We have
Yeah.
denomination like $50. We have denomination like $20. We have denomination like $10. Denomination like $5, $1, right? So
Yeah.
if I need $100, I can use 100 packets of this. Correct?
Oh, okay.
I can use 20 packets of this. I can use 10 packets
So,
of this.
so the 10 packets is what N is.
Yes.
Like, that's what he's saying that is.
Yes.
Okay.
And basically
So,
what he said that as these packets are becoming heavier and heavier, right? The number of them are reducing in the nature. So it's kind of demand and supply.
mhm,
Okay. So if I have to give an example, sneakers. A good sneaker might cost you like let us say $100, right?
okay.
Yeah.
Yeah.
And the most expensive can go up to like 10,000.
Yeah,
Yes.
sure.
So there are that is a possibility, right? But now tell
Yeah.
me how many of them are able to afford $10,000 sneakers?
100.
So there are less number of people, right?
Yeah.
And how many are able to afford $100 sneakers?
Um,
Probably more than the people who can afford $10,000 sneakers.
oh, that's what yours meant. Oh, yeah, yeah.
Am
Maybe.
I able to explain you this concept?
Yeah, yeah, yeah.
So these packets are basically what I'm trying to tell you is that these packets are getting limited as the number is becoming heavier and heavier.
So the
Okay.
number getting heavier and heavier is the energy.
Yes, more like larger energy packets, less is the number.
Oh, and then what are the packets responsible? Are the packets responsible for the intensity?
Yes.
That way, as
So
the
basically you can have
energy increases, you have less intensity.
so basically this frequency is let us say 100 is the frequency and n is the number of packet. And there are others which are like we have a frequency of 1 but there are 100 of them. Do you get me? So the intensity, the energy can be 100. Do you get me? Am I clear? I'm losing you, like the voice is breaking.
Yeah, it's clear.
Okay,
I
so
think, yeah.
now what was the next concept was we said that it was dependent on the frequency, right? That was hitting the metal surface. That decided the electron emission. Okay,
Yeah.
so that means there is certain frequency of these electrons. Okay, so the electrons have certain frequency, the light has certain frequency. When this frequency matches each other, then only the electrons are getting emitted.
Oh,
So it
okay.
is not dependent upon how much energy you are supplying, correct? It reaches a maximum, but it is a frequency that decides whether the electron will be emitted or not.
Yeah.
Okay, and that is what was proven by Einstein. Okay, so
Yeah.
Maxwell
But
said,
so
yeah,
Einstein proved Hertz's photoelectric effect.
yes.
Uh,
So he was a believer that light is made up of tiny particles,
yeah.
right? And now because of uh, Planck, right? He said that okay, there is quanta. So that means he had a belief that okay, light is made of particles. So quanta made him understand that these particles can have different energies, different frequencies. So when the frequency is matching, then only the electron is getting emitted. Okay. Any doubt with this?
So,
Okay. So what is a photon? It's a unit of light energy.
yep.
So now Einstein proposed that an electron was emitted from the surface of the metal because photon collided with the electron. During the collision, the energy of the photon transferred to the electron. Some of the transferred energy caused by the electron to break away from the atom, and the rest was converted to kinetic energy. To free an atom from the atom requires the energy from a minimum of one photon. An electron stays in place because the electrostatic force of attraction. If a single electron absorbs a single photon with the right quantity of energy, the electron can escape the metal surface. If a photon does not have enough energy, no electron can escape the metal, no matter how many photons strike it. Is it clear?
Yeah.
So the electron has to absorb the energy that should have enough kinetic energy to remove that electron from that particular atom. If that
Yeah.
doesn't happen, no electrons are emitted. So when the frequency is below a certain level called the threshold frequency, no electrons are ejected. Quantum theory has provided explanation for observation, namely the photoelectric effect and blackbody radiation, that no theory could explain. For this reason, quantum theory is one of the greatest achievements in modern science. In upcoming section, we'll learn about observation that only quantum theory has been able to explain. Okay, so understand we were talking about structure of atom. We proved or we were able to discuss till the Rutherford's model,
Yeah.
right? After Rutherford model, we entered into the classical theory of light. Why classical theory of light? To understand what is the nature of light, and with the help of nature of light, we understood the concept of quantas. And now
Yeah.
these quantas are going to help us understand the model of the atom further.
Okay.
Okay. So now let us understand what was the limitation of Rutherford's model. What was Rutherford's model? The solar system model or the planetary system, right?
Yeah.
Planetary model of the atom. Correct? So
Yep.
what is the planetary model of the atom? That We have this, like it's like the our solar system where sun is in the center and the planets are moving around the planets are moving around the sun, correct,
Oh,
in
yeah.
circular orbit, correct.
Yeah.
Now can the earth fall into the sun?
No,
Why?
because there's a force that's pushing it away. That's
Okay,
like it's like a disk or like
correct,
the sun has like gravity in space,
correct,
which is like attracting the earth, but it's not
correct.
like pushing it towards it.
Okay, so yes, the sun is getting, sorry, the earth is getting attracted towards the sun because of the gravitational force, but it has its own circulatory motion, right, which is responsible
Yeah.
for the centrifugal force, which is balancing the attraction. So it remain in its motion, right?
So if the earth didn't spin around, it would go towards the sun.
If it doesn't, if it is not spinning, but it needs to move in a circulatory motion. If it stops moving in the circulatory motion, it will go into the sun.
Okay.
It's both, like it's the revolution as well as the rotation. Both are responsible for the centrifugal force.
Okay.
They are complementing each other. That is what I would say. Okay, but I'm pretty sure that if it stops revolving, it will definitely go into the, like it will lose its position.
Yeah, it would lose its axis and then
Yeah.
it would.
Okay, so now, okay, that was about the planetary system, but when it comes to the when it comes to the atom, we have the nucleus and we have the electron. So the difference between the planetary system and the nucleus and the electron is that these are charged. Nucleus is charged and electrons are charged, right? Am I clear? Sun is not charged, earth is not charged.
Yeah.
Okay, am I clear?
Yeah.
So when the earth is moving around, sorry, when the electron is moving around the nucleus, what should happen is the electron should go on releasing energy,
Hmm.
right? And it should start accelerating towards the nucleus, and it should finally fall into the nucleus. Okay, if Rutherford's model was true, correct?
Yeah.
Does that
It's
happen
not
in
true.
nature?
Uh, no.
It doesn't, right? So that's where Bohr came into picture, and he said that probably the orbits in which the electrons are moving are quantized. Quantized means fixed energy. So till the time the electrons in the orbit moving in the orbit, no energy is lost.
Yeah.
Okay. So the model was called as Bohr-Rutherford model. So where we spoke about the presence of different orbits around the nucleus where the electrons are present. Okay. And his model was pretty successful when he spoke about hydrogen atom.
Wait, Bohr Rutherford isn't one person.
Sorry.
Bohr Rutherford is a combination of two people.
Yeah, it's combination of two people. Rutherford was a different scientist. Neil Bohr is a different scientist.
Yeah.
Okay. Okay. So his model was able to explain the spectrum of hydrogen atoms, and he was like he was able to explain that yes, there exist different orbits. He was able to give proof that okay, probably the orbits are existing where the electrons are present. Okay.
Yeah.
So mm, So what he said that till the orbit is in the till the electron is in the orbit, it will not lose energy. But if the electron has to go from one orbit to the other, it has to absorb energy. If it has to jump from higher energy orbit to lower energy orbit, it has to lose energy, which is equivalent. Does that make sense?
Yeah, that makes sense.
And these spectra, can you see over here? Red, red,
Yeah, 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 yeah.
blue, blue, right? Violet,
All of
violet.
the electron jumps emit different
So
spectra of light.
So basically, what he is trying to say is that when an electron is jumping from the higher energy orbit to a lower energy orbit, it is emitting a particular color.
Yeah,
Correct? Red is is a larger wavelength, so lower energy. Correct?
yeah.
Violet is higher wavelength, so more energy. Correct?
Isn't violet lower wavelength?
No. Yes, lower wavelength. My bad. Lower wavelength, so higher energy. I'm sorry.
Yeah,
So, okay, is that understood?
yeah,
Okay. So so far what we are able to understand is that the that there are orbits, okay, and these orbits are having different energies, okay. Am I clear?
yeah.
Now please pay attention the gaps between the first and the second orbit, second and the third, third and the fourth, fourth and the fifth, fifth and the sixth. What is happening?
The third to the second is a very large gap, and the
Yeah,
fourth to the third is a large but smaller gap, and
yeah.
the fifth to the fourth is a small gap.
So what is happening to the energy gap? It is reducing.
Yeah,
Correct. So can you see this figure 6 over here?
yeah.
So the gap between the consecutive orbit is actually reducing. Okay.
That is getting larger.
So basically first and second it is maximum, second to third it is reduced, third to fourth it is further reduced, fourth to fifth it is further reduced, fifth to sixth it is further reduced, sixth to seventh it will be further reduced. Right. So basically jumping from sixth to seventh is easy. Jumping from probably fourth to fifth is easy, fifth to sixth is easy, but jumping from first to second or first to third is relatively challenging.
Yeah,
Make sense?
yeah,
Okay. So if the electron is jumping from one orbit to the other, that is called as transition. If it is in the original state, that is called as ground state. Can you write down these two terms? Done?
yeah. That's fair.
Okay. So success and failures of Bohr model. Okay. Success and failures of the Bohr model. Mm, So success was basically I told you that it was able to explain the hydrogen spectras, right?
Yeah, 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 yeah.
So for the first 18 elements in the periodic table, Bohr model predict the first, second, third orbits can contain maximum of 2, 8, 18 respectively, and the lower energy must fill first. The corresponding Bohr other die are specifically useful for the first 20 elements of the periodic table. Okay. Beyond the first 20 element, Rutherford diagram become too cumbersome to be useful. So what I remember is the hydrogen atom was beautifully explained by Bohr Rutherford model. Okay, their model was successful till first 20 elements in the periodic table. We could explain the structure, but
That's
after
because
20, it became
that's
more and more
because
complex.
the number of shells increased.
Yes, and we'll come to that. So Bohr model of an atom initially appeared very promising for understanding behavior of atoms, but it appeared to be consistent with observed chemical physical. For example, the energy calculated for electron and hydrogen atom were very similar to the values obtained from hydrogen atom emission spectra by spectroscopy. However, the electron energies predicted by Bohr's model were not consistent for the observed data for the atoms with more than one electron. Okay.
Yeah.
Scientists eventually concluded that Bohr model did not fully describe the structure of the atom. Okay. So he was able to predict it only for hydrogen, but for other atoms we needed some other theory. Okay, okay. So now what we need to remember is that as per the current theories of the atom, electron do not actually orbit the nucleus. Okay,
Okay.
done. So that's there comes the next model, that is the quantum mechanical model of the atom. Okay. So basically, Bohr was not able to explain. So then came in Schrodinger, de Broglie, and Heisenberg. They approached the develop the explain the properties of matter. Sorry, the approach the approach they developed to explain properties of matter is called wave mechanics, or more commonly quantum mechanics.
Okay.
Okay, so quantum mechanics is what can you can write down the application of the quantum theory to explain the properties of matter, particularly electrons and atoms. We'll go slow over here to understand this concept. Okay,
Okay.
so
Just pause so I can write it.
okay, no problem. Just write down quantum mechanics.
Okay.
Okay, so now we know that like earlier, Louis de Broglie, a French physicist, okay, originated that idea that electron previously was just considered as particle has wave property. So he was the one who proposed that electron has dual behavior. Like light has dual behavior, particle and wave, electrons also have dual behavior. Okay?
Okay.
Like electron has mass, that was proven. So electron is a particle, that was proven. Okay?
Yeah.
But later on, what he proved was that each and every particle can behave as a wave. Okay,
What is it mean by wave?
Wave, what does a wave mean?
Yeah,
Is that the question?
basically.
Okay, so wave is basically something which requires a medium to move from one position to the other.
Okay.
Okay, and uh, like, have you ever tried to throw a stone in a lake?
Yeah, yeah, like skipping rocks.
Yes, so there can, do you see that there are some up and downs that are generated because of that?
Yeah, like it bounces on the
No,
water.
not the stone, but the water. What has happened to the water?
Oh, like
The
it
the
it
concentric
ripples.
circles when you try to, yeah, the whirlpools, or when you try to drop a stone into the water, do you see that there are waves that are generated?
Yeah.
So that is what is a wave. It has a up, like can you see this image over here?
Oh, like yeah, 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 yeah. It has a I don't know what it's exactly called, but like the peak and then the valley.
So yeah, so troughs and even I forgot the word. Okay, we
Yeah,
will we will learn it
seen it
further. Don't
before.
worry.
Yeah.
Okay, so yeah, so wave is basically, yes, as you know that there is a peak and there is a shallow, or there is a valley, right? Crest and troughs. Okay,
Yeah.
so now what de Broglie said was any particle, any moving object in the universe can behave like a wave.
Okay.
Okay, the problem with the larger particle is that their mass is huge, and because their mass is huge, their wavelength is so small that it is negligible. Okay, but
Yeah.
electron is a particle which has mass which is so small that it has wavelength which is recordable. Okay, am I clear with what I said?
Yeah.
So when like I don't know, where do you play baseball? Which sport do you play?
Badminton.
Okay, so the shuttlecock, does it go like a wave, like up down and then go to the other court? Does,
It goes up and down.
yeah, it goes up and down like a projectile, correct?
Yeah.
But it doesn't go like this,
No.
right? So that is the wave nature. Okay. So
Yeah.
what Schrodinger said that even your shuttlecock travels in the wave form. Okay.
Yeah, but it's too big to be
Yes.
able to
So
notice it.
so basically this, in this projection, the wave is so tiny that it is not even appearing. But when it comes to an electron, when it is thrown like this way, the wave nature is prominent.
So the smaller the mass, the
Wave nature becomes more prominent. So electron has mass, so it's a particle. The mass is negligible. Because of that, it can behave like a wave, as per de Broglie. Correct?
oh, okay.
Okay. Then what Schrodinger did was he approached the problem of atomic structure by focusing on the wave properties of the electron.
Yeah.
Okay. So Schrodinger and de Broglie, an electron bound to a nucleus in an atom resembled like a standing wave. Okay.
Yeah, that makes sense.
So there the began research of description of the atom based on the wave behavior instead of the particle behavior. Okay, so strings of an instrument such as guitar and violins are attached at both ends. Similar that electron is attached to the nucleus. It vibrates and produces musical tones. So the wave produced by the plucking are standing waves. They are called standing waves because they appear stationary. Correct? Otherwise, waves are moving. Am I clear? Hello?
Hello?
Is the concept of standing wave clear?
Yeah,
Okay, or what you can do is you can tie a rope to a doorknob and try to move it up and down. Okay, so
yeah,
what you will see is that there is a wave that is generated. It, although it is moving, but it will appear to you as like it's a standing wave.
yeah.
Okay, now they are called standing because they appear to be stationary. The motion of the string are a combination of simple waves, right? So one move, first it will move forward and backward. So basically that is what is your standing wave, correct? Now the black dots, figure 1, represent the nodes or a point of zero lateral displacement or for a given wave. So here there is zero displacement, correct? So this region is called as node. Okay, between two nodes at a point where the amplitude of the wave is at its maximum is an antinode.
So the first one is an amplinode or antinode.
Correct.
Yeah,
So between two nodes at point where the amplitude of the wave is at its maximum is the antinode. Note there are limitations on the allowed wavelengths of the standing wave. Each end of the string is fixed, so there is always a node at each end. So obviously there is a node at each end, and the number of waves that can, like number of crest and troughs that it can have is fixed. It cannot have more than a specific number. Does that make sense?
I think so, yeah.
Because the string is connected at both the ends, right? So either there is only a specific number of waves that it can have.
Yeah.
Okay. So this means that there must be a whole number of half wavelengths in any of the allowed motion of the string. So here you have two half, here you have three half, here you have one half. Then only you can say that the wave is actually a real wave. You
Yeah,
cannot have fractions, correct?
yeah.
Okay. You cannot have fractions. Is that clear?
Wait, are wavelengths formed because of gravity?
Are wavelength form because of gravity? Mm, what type of wave? There are gravitational waves too.
And I'm like thinking about the badminton shuttlecock. It looks similar to the one half wavelength. Like
Sorry.
when you like, you know, badminton?
No, I'm not aware of that concept.
No, badminton, the
Oh,
sport.
badminton, yes.
Yeah, yeah, yeah. So when you're hitting it and it goes like up and then down over the net, it looks like the one half wavelength and it's
So
caused by gravity.
no, no, no. Okay, now that is only a projectile motion. It goes from here and it goes down. It is not coming back. So this is a wave, standing wave.
Oh,
Okay, this is a wave. This is a wave. Does that make sense?
yeah, I think it does.
So you can say that is a half wave. The other half was not existing. Okay.
Yeah,
So it's basically we call it as a projectile. Okay.
yeah.
So there's only one motion, goes up and then down. So
Yeah,
basic.
that makes sense. Yeah,
Okay.
I can understand it.
So just check this. Now there are two half waves, correct?
Yeah,
And they are appearing as stationary. So we don't see this nature in badminton,
no,
correct? So for a wave at both end, it needs to be tied. Okay. So Schrodinger and de Broglie took the idea of standing waves and applied it to the electron in a hydrogen atom. In their model, the electron is a circular standing wave around the nucleus. Circular standing wave consists of wavelengths that are multiples of whole numbers. Only certain circular orbits have a circumference into which the whole number of wavelengths can fit. Any other orbits of the standing electron wave are not allowed because they would cause the standing wave to cancel out or collapse. That it undergoes destructive interference. The model seems like possible explanation for the observed quantization of hydrogen atom. Whole number multiples of wavelength correspond to multiple fixed quanta of energy that the electron can have in the hydrogen atom. However, the new question that this model raised was where the electron is located in the hydrogen atom. So they were able to prove the existence of the quantized energy, right? They somehow proved the shells,
Okay.
right? So the hydrogen electron visually visualized as a standing wave around the nucleus. In A and B, the circumference of particular circular orbit corresponds to the whole number, correct, of wavelengths.
Wait,
So
so
it
the red part is the electron moving around the nucleus?
no, the red part is trying to tell you that yes, the standing wave exists because it is fitting the calculations. Okay, so when we say that okay, two half wavelength exist, here what do we see? How many? Four, right? So do you see
Yeah.
one, two, three, four? So four half wavelength exist, five half wavelength exist. So it is in telling you that okay, shell with n is equal to 1 is existing, shell with n is equal to 2 is existing, shell with n is equal to 3 is existing.
Oh,
Okay.
is this trying to prove that you can't get a shell that's a decimal?
Yes, that is also what we proved over here, that we cannot have a fraction,
Oh, okay.
right? So the same concept was applied to the hydrogen spectras. Okay.
Yeah.
Now, now comes the next question where the electron is. Okay. So in order to explain where the electrons are present, we there is a new term that is coined that is called as the orbital, the region around the nucleus where the electron has probability of being found. Okay, can you write down that?
I remember learning about this last year,
Okay.
about quantum numbers.
Last year quantum numbers, grade 11.
Yeah.
So the
Like,
quantum numbers are easy, but the like those are easy to understand, but how that was originated, that is a concept that we are trying to understand now. So for Schrodinger, what do you need to understand is that there is something called as a wave nature that they considered. There were standing waves. Standing waves will have whole number, right? When the
yeah.
standing waves have whole number, similarly hydrogen spectra, the whole like the presence of the shells were proven. The energy levels were explained. Okay, any doubt? Now still where the electron is present, that is not explained.
Yeah.
Okay, to explain that electron, Schrodinger gave Schrodinger wave equation. So Schrodinger work on quant has led development mathematical equation called Schrodinger
Wait,
wave equation.
sorry to stop you, but is it up to 8, the meeting?
Yeah,
Oh, right now it is 8 o'clock.
okay, no problem. So let us continue this in the next class.
Yeah. Sounds good.
Okay, no problem.
Okay.
Bye.
See you next week. Bye.
Yeah, bye.